Most people looking at Tesla's Terafab renders fixated on the headline numbers. 100 million square feet, a targeted 1 terawatt of AI compute a year, enough to theoretically produce somewhere between 100 and 200 billion custom AI chips and memory units annually. Almost nobody focused on the giant circle sitting dead center in the blueprint. When one ex-user asked Musk directly whether there was a particle accelerator underneath it, his reply was 6 letters, FEL FTW, free electron laser for the win. That's a genuinely strange thing to build a chip factory around, and it's worth understanding exactly why rather than treating it as another throwaway Musk post. Start with the actual bottleneck Terafab is trying to solve. Tesla's push into Optimus and robo-taxi, plus SpaceX's ambitions for Starlink and space-based AI, all share the same constraint: not enough AI chips, and not because of ordinary supply chain friction. Musk has said the world's current chip output might satisfy only around 2% of what the Tesla SpaceX ecosystem could eventually demand. That's a manufacturing capacity problem at the scale of the entire semiconductor industry, not a shortage Tesla can order its way out of. Terafab's target specs reflect that. Roughly 100 million square feet, about 10 times Gigafactory Texas, envisioned as one integrated complex handling chip logic, high-speed memory, and advanced packaging together rather than shipping wafers between separate specialized fabs the way the industry does today. The central circle is where things get genuinely technical, and it's worth slowing down here rather than skipping past it. Cutting-edge chips depend on EUV lithography, extreme ultraviolet light at around a 13.5 nanometer wavelength, used to print transistor-scale structures onto silicon wafers with atomic-level precision. Today's EUV systems generate that light by blasting tiny tin droplets with a high-powered laser until they turn into an ultra-hot plasma, and while the approach works, it's energy-hungry and throws off debris that can damage the extremely expensive mirror systems inside the machine over time. A free electron laser is a fundamentally different approach. Electrons accelerated to nearly light speed, get forced through a specialized array of magnets called an undulator, and as they're made to oscillate, they emit light. With enough precision, those light signals can interact coherently and be tuned into exactly the EUV wavelength chip making needs, without tin, plasma, or the debris problem anywhere in the process. The reason this could matter at Terafab's scale specifically is structural, not just about avoiding tin debris. In a conventional fab, every single EUV lithography machine needs its own dedicated light source, and that becomes a real constraint once you're running the hundreds of thousands of wafers per month Terafab is targeting. A centralized free electron laser feeding multiple lithography systems would turn the light source from a per-machine bottleneck into shared infrastructure serving the entire facility, no debris buildup, and in theory, higher power output and better energy efficiency at scale. That's the actual bet behind the circle. It's also worth saying plainly, unproven at this scale. Nobody has run a free electron laser as production EUV infrastructure for a commercial fab before, so this is a real technical wager, not a settled engineering choice. Tesla isn't betting entirely on its own inexperience to pull this off either, which matters given how unforgiving this industry is of mistakes. Building an advanced fab is a completely different discipline than building cars or rockets. Ultra-clean environments, EUV tools costing hundreds of millions of dollars each, extremely pure chemicals, and atomic-level precision where a single defect can ruin an entire wafer batch outright. That's why Intel's involvement matters beyond just having its name attached to the project. Tesla brought in Gary Jang, a 17-year Intel manufacturing veteran who previously ran Intel's 18A process operations, as Terafab's first-name director, which reads as a genuine attempt to import real fab discipline rather than assume that EV and rocket manufacturing instincts transfer directly to semiconductors. Power turns out to be the other genuine surprise in the plan. Running a facility this size at its compute target requires enormous, uninterrupted electricity, and according to recent filings out of Grimes County, SpaceX plans to build its own natural gas power plants combined with large-scale battery storage, rather than lean primarily on the Texas grid or on solar. That's a notable choice given Tesla's own brand is built around EVs, Powerwall, and Megapack grid storage, but the logic is practical. A fab needs what the industry calls firm power, meaning continuous reliable supply, since a major outage can damage wafers and equipment mid-process. Solar is inherently intermittent, and hitting Terafab's power draw on solar plus storage alone would mean an enormous, extremely expensive battery buffer from day one. Building dedicated gas plants also means SpaceX isn't waiting years for a grid interconnection queue and isn't competing for capacity against the wave of other AI data centers being built across the country right now. Energy access is becoming as real a constraint on the AI race as chip supply itself. The production targets are aggressive by any standard. An initial run around 100,000 wafers a month, with a long-term goal of 1 million wafers monthly, a scale that, if actually reached, would make Terafab less a Tesla-only supplier and more one of the largest semiconductor hubs on the planet. Reported figures put the first phase at roughly $16.8 billion, with total investment across all planned phases potentially reaching $119 billion, which would make it the most expensive project Musk has ever attempted, ahead of anything else in his portfolio. The jobs figure attached to the project is around 3,000 in the surrounding Texas area. All of this compute is meant to feed two specific chip families. AI-5, moving toward AI-6 and AI-7, is aimed at powering full self-driving robo-taxi and Optimus, the vehicles and robots needing real-time physical world processing. Separately, the D3 family is being developed specifically for Starlink and AI applications in space, engineered to survive radiation, extreme temperature swings, and vacuum conditions. Earth-based chips never have to handle. Those two chip lines are effectively the actual product Terafab exists to manufacture. The factory is infrastructure, not the end goal. So the honest version of the question isn't whether the circle is real. It clearly is, and Musk has confirmed what it's meant to be. It's whether a free electron laser can actually deliver production-grade EUV light reliably at industrial scale, something that's never been done commercially before, or whether it stays a compelling idea that doesn't survive contact with real manufacturing yields. That's the detail worth watching as Terafab moves from blueprint to construction. Subscribe to the Tesla Breakdown if you want to see which way it breaks.